Am I audible, everyone?
Yes, sir.
Okay, good. Thanks. Uh, okay. Good evening, everyone. Welcome to the week 8 problem discussion session of Discrete Mathematics. My name is Bhabhi Rai. Uh, so, today's topic is graph theory. This week's topic is graph theory, and last week's topic was also graph theory, but it was on a more introductory level. Now we are going deeper into graph theory this time. I'm going to call it graph theory 2. Okay, so I'll not dabble too much in the details, but just for the sake of it, what is a graph? A graph is a set of vertices and edges. Okay, and vertices can be represented by these nodes, and edges can be represented by these these lines between nodes, which show the relationship between two edges. So this shows that one is related to two is related to three, and so on. So it is a way of describing relations, right? So we saw a bit about graph last time, and this time, and also like we saw the types of graph representations, right? I think we saw adjacency matrix already, but there is something called incidence matrix. Okay. Uh, okay. So let's say this is the graph given to you. What will be your adjacency matrix? Okay. So you'll just have vertices as rows, columns, and vertices as the rows of your matrix. Okay. So for example, if let's say, okay, for example, let's say this is your matrix, and I'll label them 1, 2, 3, 4 because these are your vertices 1, 2, 3, and 4, right? And I'll label the rows as 1, 2, 3, 4. Okay. And then if an edge exists between the labels, okay, of the vertices, then we'll write a 1, otherwise a 0. For example, is 1 connected to 1? No, so 0. Is 1 connected to 2? In our graph, yes, 1 is connected to 2, so I'm going to write a 1 here. Is 1 connected to 3? No, 0. 1 is connected to 4? Yes, via this edge, right? So I'm going to put an edge between 1 and 4 here. So, and I'll continue. 2 is connected to 1, and 2 is connected to 4. 0 is 0. 3 is connected to 4, right, and nothing else. 4 is connected to 1, and 4 is connected to 2, and nothing else. So this is what is called the adjacency matrix. We looked at it in last week also, so just giving you a bit of revision. But what is an incidence matrix? An incidence matrix, or sometimes it's also called the edge incidence matrix. Okay, an edge incidence matrix does not talk about relationships between vertices to vertices directly. Rather, our subject, we choose to represent our edges. Okay, what do I mean by that? My columns, my rows are actually edges this time. Okay, and let me label these edges. This is called E1, this is called E2, this is called E3, this is called E4. See, now what I'll do is I'll label the rows as E1, E2, E3, E4, and I'll label the columns as vertices this time. Okay, again, so 1, 2, 3, 4. So let me draw it. Now if an edge exists between, if an edge is incident on that particular vertex, then I'll put a 1. So is E1 incident on 1? Yes. Is E1 incident on 2? Yes. Otherwise 0. Is E2 incident on 1? Yes. And E2 is incident on 4. Okay. And otherwise 0. E3 is incident on 2 and 4. And E4 is incident on E4 is incident on 3 and 4. Right. So 3, 4. This is what is called your edge incidence matrix. Okay. Now, both are equivalent in terms of information stored, but a lot of times adjacency matrix is actually a smaller representation. A lot of times. Okay. And why? Because the number of edges, okay, or rather the if the graph is connected, then the number of vertices is less than the number of edges, right? So the size of this is number of vertices times number of vertices, but this one has a size of m cross n, as you can see, because there are m edges, number of edges. So yeah, these are some kind of things pertaining to graph representation. And this you have a generalization of graphs called hypergraphs. Okay, and hypergraphs actually use this type of representation, this edge incidence matrix. You might ask, like, why do we even care if we already have adjacency matrix, which is supposedly more compressed form of representing? Then I mean, it is difficult to represent hypergraphs using the first technique. Okay. Anyway, let's move on. Just a simple question again on graph representation. The question says, oh, okay. So I'll cut this out. There's nothing true or false about the statement. The statement says, write the adjacency matrix of C, write the incidence matrix of G. So the adjacency matrix of G, again, it's pretty straightforward. I'll label the columns A, B, C, D, E, because these are my vertices, right? And I'll label the rows as A, B, C, D, E. Next, if I'll check what is A incident on. A is incident on C and E. So C and E have forms. What is B incident on? B is incident on C and D. So C and D. Others are 0. What is C incident on? C is incident on A and D. Right? So A and D. What is D incident on? D is incident on B and C. What is E incident on? Oh, sorry, this is E. This is E. Okay, it was not clear to me, and may not be clear to you as well. So E is incident on. Okay, C is incident on A and D. That is correct. No. Okay, D is fine. C is incident on B and A. Right. And finally, E is incident on A and D. Okay. Now, what is the incidence matrix of G? Well, my rows are my edges. Okay, but there are no labelings given, so you can use your own labeling. Let's say this is E1, E2, E3, E4, E5. Now, simply just make your rows as your edges and columns as your vertices. So E is connected to B and C. E2 is connected to B and D. And E3 is connected to C and A. E4, okay, is connected to A and E. And E5, the final one, is connected to D and E. So this is your answer. This is the answer for A, this is the answer for B. I hope this was clear. So that is all that I would like to ask in terms of the representation of graphs. We'll move on to some more interesting stuff. Okay, bipartite graphs. Okay, a graph is bipartite if the vertex set I can partition. Okay, if anyone remembers, partition meaning I can divide the set, divide this original set into two sets. Okay, or more sets, but in this case 2 sets, such that they do not share any vertices. That is what partition means, right? 2 sets that don't share vertices. Okay, let's call them V1 and V2. And V1 does not share vertices in V1 do not share edges with each other. For example, this is the first partition, and this is the second partition. And you can see that there are no edges between the vertices in the same partition, right? So is this bipartite? Yes, this is bipartite. But look at this case. If I do a partition like this is getting shared. Okay, this edge is getting shared. This edge is getting shared here. Now let's say I don't choose, let's say you might say, oh, but I can choose something else. No, let's say I choose this as one set and this as the other set. Okay, this set is not sharing, so this is good. But this side on the left, this L-shaped thing, is sharing edges here and here with each other in the same set, in the same partition. So this is also not working out. And you may try other things. This one. Okay, and it's not working out. So there is a fast way to check this. Okay, I mean, not in all cases, but yeah, definitely in a lot of cases this is possible to check. And this graph is actually not bipartite. So I'm going to exactly address that question. Okay, how do you quickly check whether a graph is bipartite? So yeah, I would first like you guys to think about it. My question is the following graph bipartite? So can you try it once? I can show this just in case Bipartite means divide it into two partitions such that vertices from the same partitions do not have edges among them. Okay, so is this graph bipartite? To give you a, okay, Akansha says no. Okay. Well, to give you a hint, there is a certain fact about bipartite graphs which you can use. And a bipartite graph has, or in other words, does not have a certain structure. So if it does not have some structure within it, then you can tell whether it's bipartite or not. So, Akanksha, can you tell me why this is you are saying no?
Sir, cause it has odd cycle.
Yeah. Good. That's the fact. Good. The fact is, any bipartite. Okay. Or I'd rather say it as, if a bipartite graph has odd cycles, which means the length of the cycle, okay, number of edges in the cycle, number of edges in cycle is odd, then it is not bipartite. Okay. Now, why? Because look at this graph: B to A to C, B to C. This is an odd cycle. There are three edges there, which is odd. 3 is an odd number. So B to A to C is an odd cycle, which means, let's call this graph G. G is not bipartite. Okay. I did not mention, I told you guys to try it first because this was done in the lectures also. But the concept is quite simple. It just means that, if a graph is bipartite, I can, partition it into two vertex sets. Let's call it L and R. And if the bipartite graph were to have a cycle, okay, my claim is that it can only be even. Why? Let's try to build a cycle. Here is one edge, okay, starting from this edge, this vertex, and here is one edge. Okay, why am I drawing an edge to the left? Because if I draw an edge here, it will no more be bipartite because I'm having edges in the same partition, right? And next, what I do is I can only move left, okay, and let's say I move here, and to make a cycle I need to go like this. How many edges are there? 4, which is even. But let's say I want to avoid that case, then I go here again, but now I'm not forming a cycle. So in order to form a cycle, let's say I move here, okay, it is not possible to form a cycle by ending up in the right end, because I'll always end up doing odd number of steps. So I'll do another even number of steps. I make a cycle here. Okay. So in order to land at the same vertex, okay, in order to form a cycle, I need to make how many even number of alternations. I need to make even number of alternations. Okay. So this is the reason why it is a bipartite graph. It is if it has a cycle, then it should be necessarily an odd cycle. Okay. So yeah, I mean, in this particular week, I think there are a lot of terms floating in. So I'll be giving slight introductions to that also. For example, complement of a graph. So before, like, we did what a complement of a set is, right? For example, if I have a set A, then the A bar is universe minus A, right? And this is A bar. Similarly, if I have a graph G, okay, this is G. G bar is the complete graph, which is my universe here, okay. Kn, okay, how many edges are there? 4. How many vertices are there? 4. Complete graph and 4 vertices minus my G. It's like universe minus A. But the main thing is, in a complement, the vertex set remains the same. I'm not deleting vertices, I'm just deleting edges. What do I mean by that? Okay. What do I mean by that? Here I have an example of a graph, okay, on 4 vertices. This is what I call G. I will draw a complete graph on 4 vertices. Now what I'll do, in order to form G bar, I'll keep the vertex set as same, and I'll remove all the edges that are in common. Okay, so okay, and I'll name it 1, 2, 3, 4. This is nothing but K4. So what are common? This is common, this is common, this is common. So I'll remove those edges. So what will I get? I'll get this edge, and I'll keep the edges which are not removed, which are not common. Oh, and this is also not. So here is an example. So this is complement. Another example is this particular graph. This is one graph. Okay. Now I'll make a complete graph on 3 vertices. Kn. Okay. Okay, sorry. This is a complete graph on 3 vertices, right? Now what I'll do is I'll remove all the edges which are in common. Let's say this is 1, 2, 3. What edges are in common? This is an edge in common, right? So then what do I get? Removing that edge will give me this particular graph. 1, 2, 3. Okay, this is what is meant by complement. Now, let us do one question on complement. Okay, let's say G is a connected graph, okay, which is self-complementary. Now, what is meant by self-complementary? G is isomorphic to its complement. That is, if I complement the graph, if I take a complement, then G will look the same. Okay, G bar will look the same as G. G bar is the notation used to show complement of G. Okay. Which of the following statements are true about G and G bar? Statement 1 says, for a vertex V, the degree of V in the graph G plus the degree of O. Okay, sorry, there's a mistake here. So this should be same vertex. Degree of the same vertex in the complement is equal to n minus 1. Okay. Statement 2 says, for a vertex V, degree of graph G minus degree of G bar V is equal to 0. And the other says G bar is disconnected. Statement 3 says G bar is self-complementary. G bar is also self-complementary. And 4 says G bar is disconnected. Now, which of the statements are true here? So you can think for a while about this, or you can, if you found that a certain statement is definitely true, then you can tell me that okay, statement 1 is definitely true, and then go ahead. Okay, so self-complementary. Okay, I can give you an example of self-complementary right here. So this is an example of a self-complementary graph. Why? Because this and this are isomorphic. If I just move around the vertices, flip these two vertices, okay, then I'll get the same graph, isomorphic graphs. So now the question is, such a self-complementary graph is given to you. The sum of the degrees of the same vertex, okay, in each of those graphs, is it equal to n minus 1? The difference between the vertex is 0. G bar is also self-complementary. G bar is disconnected. So which of these are true? Okay, Akanksha says C. Okay, good. Let's wait. Divya? Okay. Let's see what the correct answer is. So let's check the first answers. Statement 1. Okay. For a vertex, the sum of the degrees between its complement and itself is n minus 1. Okay, let's see. Let's just focus on one vertex V. Okay. And let's say this is the vertex, and this is in G, and this is in the complete graph K N. Okay, and let's say Kn is 6, K6. Okay, in the complete graph of 6 vertices, let's say, and G has, let's say, 6 vertices. And how do I obtain the complement? If I take a G bar, then I'll remove whatever is common, right? So if there are four edges here, so I'll remove 4 edges from here, right? When I take the complement, that's how it works. So that particular vertex will have only two. Okay, so this is not key 6, this has to be key 7. Yeah, there are only two, what do you call, edges, right? This observation is clear, I hope. So, this is true for all graphs, as you can see, okay? And next, what are you saying? You are adding up 4 and 2. There are 4 edges. There are 2 edges, right? And 4 plus 2 equals 6, right? And therefore you have that, since there were 7 vertices in the beginning, okay, 7 vertices, the answer is like n minus 1 should be true. Well, the other way of looking at it is, any vertex in the maximum will have n minus 1, n minus 1 degree, maximum degree that can have. Now, this is especially true when it is a complete graph. If it is a complete graph, since it is every vertex is connected to all the n minus 1 other vertices, the degree is exactly equal to n minus 1, right? Now what I do is, from the n minus 1, I'll obviously remove while taking the complementation, let's say 2 vertices or 3 vertices, however you want, and whatever remains will actually be the number of vertices in the complement graph. So it is true that the sum of the degrees is equal to n minus 1, right? I hope this is clear, but please let me know, okay, if something is not very clear. Let's check the other statement. Statement 2. For a vertex V, the degree of G, V in G, and degree of V in G bar is equal to 0. Now here again we'll use the idea of self-complementary here, okay? Now what we'll do is, let's say this is V in G and this is V in G. And let's say this one has 4 and this one has 5. Well, and if I imagine the whole graph, you will say obviously this cannot be, this cannot be, self-complementary. Why? Because this the vertices out here and here, okay, are of unequal degrees. If they are of unequal degrees, how can they be isomorphic? So that is the idea. So therefore what we have is degree of G, V on G, okay, is equal to degree of G bar. Since it is self-complementary, it should necessarily be equal. So degree of G of V minus degree of V in G bar is equal to 0. So statement 2 also holds. Let's look at statement 3. G bar is also self-complementary. Well, statement 3, G bar is also self-complementary, and this is quite obvious that if I have a graph and I take its complement, let's say, and then I take its complement again, I'm going to get the original graph. Why is it? Because here I'm removing all the edges in common, and now what I'm doing, I'm adding all the edges in common and removing what I had done before. So you can try this yourself, okay? I'm not going to dabble too much into it, but statement 3 is, you'll find out that statement 3 is true. Taking complement 2 times gives the same thing, in other words. Finally, G bar is disconnected. Now this one is a bit tricky. So statement 4. G bar is disconnected. And the original assumption was, and G is self-complementary. Now we'll analyze this. Okay, let's say G bar is disconnected. This is definitely not true from question. Sorry, G is disconnected. This is not definitely not true because the graph was connected. Okay, now let's say G is connected, and if G is connected, then we know that on complementing we can get a connected graph or a disconnected graph. Now we are the statement is saying it is disconnected, but how can you say the question is saying it is definitely not connected, but how can you say some graph is isomorphic to another graph such that the first graph is connected and second is disconnected? So this is the first graph. We are saying that this graph, which has 3 components, okay, this is disconnected, is same as this is G bar. This is congruent to G bar. Sorry, isomorphic to G. How can we say that? Because we can always find 2 edges which are not connected here, but here obviously we can find 2. Every vertex is connected. So this is absurd, and this is a contradiction. So statement 4 is not true. Right? By question we have that G is connected, and its complement may be connected or disconnected, but the statement says G bar is disconnected. Is it true? But if G bar is disconnected, how can G and G bar be isomorphic to each other? How can G and G bar look same? So that is the idea. So obviously the answer is C. Okay. I hope that is clear. Divya, is that clear? The final part especially.
Yes, sir. Clear, sir.
Oh, okay, good. So yeah, so statement 4 is false. So yeah, C is the answer. That's right. Okay, moving on. Okay, Eulerian and Hamiltonian graphs. Okay, an Eulerian graph is one which has an Eulerian circuit. Now, what is an Eulerian circuit? It is a circuit covering all, sorry, not vertices, edges. So you might have seen it in the lectures, right? A famous problem called the 7 bridges of Königsberg. So, for example, okay, is this graph Eulerian? Okay, this graph is Eulerian. No. Let's see. 3. Now it's Eulerian. Yeah. So, how do I visit all edges here? I can do this, 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 this. No. Without repeating any edges. Yeah, I can do this. I can go here to here, here to here. Then I go here, 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 and here. Okay. What I mean here is that without repeating to starting at a vertex, okay, and this is my start vertex that I've chosen. Starting at any vertex actually. Okay, can you give me a starting vertex? That is also good. So can there exist a vertex such that there exists a cycle which I can traverse? Okay, there exists a path rather, okay, where I can traverse each and every edge and come back to the vertex where I started in. So this is an example. Okay, so here I began from this vertex, took this edge, and took this edge. Okay, took this edge, and here. Then I came back to the vertex I started from. So such a path is actually called an Eulerian circuit. Okay, and such a graph is called an Euler graph. And what is a Hamiltonian cycle? Hamiltonian is a cycle. A Hamiltonian cycle is a cycle covering all vertices. For example, what is this graph called? It's a complete graph on 4 vertices, which is also called K4. So does it have a Hamiltonian cycle? Yes. This is the Hamiltonian cycle. I'll just take the outer cycle and it will cover all the vertices. So K4 is a Hamiltonian graph. Okay. Next, there is a condition on Euler graph. Okay, there's a nice property. A graph is Eulerian. That is, it has a path which visits all the edges and comes back. Okay, if and only if graph is connected. This one is obvious. Otherwise, how will you visit all the edges, right? And next thing is degree of all vertices are even. Okay, for example, let's see here. This degree is 4. This degree is 2 even. This degree is 4. And this degree is also 4. Even. All the degrees are even. So you can directly see. Here, is this Eulerian? Well, this has degree 3. So not all the vertices have even degree. So this is definitely not Eulerian. But it is Hamiltonian. Well, I'm kind of giving away some information for the next question, but still, you can see it here. So let's solve this question. Which of the following graphs are Eulerian? Okay. In other words, which of the following graphs have an Eulerian circuit, that is a path which covers all the edges and comes back. So please try this and let me know. Okay, Akanksha says A. Divya says A. Okay. Okay, good. That's right. So, yeah, the quick way to check it is there is a long way, and that is, you try all the paths and so on. But we have some tools to make our process faster, and the tools is obviously this particular fact. Okay, a graph is Eulerian if and only if connected and degree are all even. Well, it is connected. All of them are connected, but degree is all even. Let's use that fact. Okay. So, what is the degree here? Of B is 4, C has degree 2, D has degree 2, A has degree 4, and E has degree 2. Okay. Now, this is all even, so this is good. Any more graphs which satisfy? Well, B has degree 3, already disqualified. Well, here A has degree 3, so already this is disqualified. And here B has 3, and E has 1. Here also C has 1, so already disqualified. So the answer is A. Yeah, graph A. So yeah, the answer is correct. But so now think about those things. Let's observe this question. Okay, which of the following statements are true about Eulerian and Hamiltonian graphs? If a graph is Eulerian, then it is Hamiltonian. If a graph is Hamiltonian, then it is Eulerian. There are graphs that are both Eulerian and Hamiltonian. So which of these statements are true? So think about it. Maybe try making examples. Okay. So what is the relationship between Eulerian and Hamiltonian graphs, or do they even have a relationship or not? So which of these statements are correct? I'll give you a few more time. Okay. Yeah, let's analyze these. Well, okay. So if I have to prove a statement, then it is quite difficult. But if I have to disprove a statement, then all I need is a counter example, right? So maybe it is easier to provide a counter example. So if a graph is Eulerian, then it is Hamiltonian. So let us try to disprove this statement first. Okay. Eulerian, then Hamiltonian. So I need to create a graph which is Eulerian but not Hamiltonian. Right. So what I'll do is, let me start making the graph. Okay. Let's say I do this, I do this, I do this, I do this and this. Then clearly it is Eulerian. I can use this particular path to say that all the edges are visited, and clearly the same thing is a Hamiltonian cycle also, because all the vertices are visited. So such an example will not work. But the advantage of Eulerian graphs always is that I can repeat vertices. Okay. But I'm not allowed to repeat edges. But Hamiltonian paths, since it is a cycle, both should not be repeated. So this is a more difficult thing. So what I'll simply do is I'll create a common meeting point. Okay. Now I'll observe that if I move here, 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 until here, then this is definitely Eulerian, right? But is this Hamiltonian? That is, can I find a cycle which visits all the vertices? I definitely cannot, because this is a cycle, this is a cycle, but there is no bigger cycle. So at the max, any cycle can visit only 3 vertices, right? Because this red one is not a cycle, because they intersect at a point. A cycle is not supposed to, you know, intersect and then diverge. So this is not Hamiltonian. So statement 1 is false. Let's look at statement 2. Statement 2 says Hamiltonian, then Eulerian. I think this example was given in the lectures also. So the example is as follows. Let's take a graph which is Hamiltonian. This is the simplest graph which is Hamiltonian, right? And let's say but this is Eulerian also, because I have a path that visits all the edges and it comes back. So I need to somehow add something like this edge, so that some edge is not possible to visit. Clearly this is Hamiltonian because there is a cycle here. Is this Eulerian? Yes. Why? Because there is a vertex. This is not Eulerian. Why? Because there is a vertex where degree is 3. But this is Hamiltonian because of this path, this cycle, which visits all the vertices. So Hamiltonian, but not Eulerian. So statement 2 is also false. Now C says statement 1 okay. Now let's verify statement 3. So this one, I will ask you for an example, okay? There are graphs that are both Eulerian and Hamiltonian. So can you quickly tell me, can you think and tell me an example of a graph which is both Hamiltonian as well as Eulerian?
C4.
Yeah, good. A cycle, that's right, C4. So this is C4. And this is a Hamiltonian cycle, and this same cycle, okay, also serves as a Eulerian circuit, because all the edges are obtained. So this is Eulerian as well as Hamiltonian, as it has a Hamiltonian path. Both are there, so it is a Hamiltonian as well as Eulerian. So statement 3 is correct. So statement 3 is true, and therefore answer is B. So I hope that is fine until now. Okay. Yeah, so 1 and 2 are false, and only statement 3 is true. Okay. So let's move on. So next we'll look at Dirac's theorem. I mean, Or's theorem is also there, but I didn't form a question based on it, so I'm not putting here. So Dirac's theorem is the following. It says that if every vertex in the graph has degree at least n by 2, then G is Hamiltonian. Okay. And so yeah, this is a straightforward question based on Dirac's theorem. Okay. So G is a 5 regular graph on 9 vertices. Okay. Does G contain a Hamiltonian cycle? This is a simple question. So this is a direct application of Dirac's theorem. Can you tell me? So Dirac's theorem says that if every vertex has degree at least n by 2, then G is Hamiltonian. Okay, Akansha says yes. Bhumati says yes. Okay. Okay, good. Yeah. The answer is correct. Yes, it does have a Hamiltonian cycle. Why? It's just straightforward application of Dirac's theorem. Dirac's theorem says all the vertices have at least 10 by 2 degree. So let's look at degrees of each vertices. So G is a 5 regular graph. This is 5 regular. What is meant by a regular graph? All the vertices have same degree. What is meant by a 5 regular graph? All the vertices have degree 5. 5 regular means for all vertices degree is exactly equal to 5. So that is one thing. Next, what information do you have? N, the number of vertices. Okay. The number of vertices n is 9. So 9 by 2 equals 4.5. So clearly degree of each vertex, which is equal to 5, is at most n by 2, which is 4.5. This is for all the vertices in B, which means by Dirac's theorem the graph is Hamiltonian. Okay, good. Yeah, so that is the straightforward application. So next we'll move on to planarity. Okay, now a graph is called planar if it can be drawn without intersecting edges. For example, this is a planar graph. Okay, this is a planar graph, and this is a planar graph, and this is a planar graph. Okay, I mean, why? Because I can take this edge, okay, this edge, and I can stretch it until here, and still the vertices don't, till the edges won't intersect. But now, okay, if I put a, okay, no, yeah, this is still, but an example of a non-planar graph would be something like this. Okay. So this going to this. Yeah, next this is connected to this 3. Is this non-planar? This is not non-planar. Okay, a direct example I can give is just K33. This is a very well known non-planar graph. So you cannot draw it so that all the edges don't intersect. I can pull each edge here and there. I can stretch it as much as I want, but I will not get something like this. And you saw it in the lectures also, right? If it has a K33 or a K5, then it is definitely not a planar graph, right? So, well, if a graph is planar, then it satisfies these following properties: the number of vertices minus the number of edges plus the number of regions. So This is what are called the regions. Okay, these boundaries that separate. Okay, these faces, these are also called faces. These are called the regions. And also, mind you, the regions, this outer region is also counted. So let us try that. In this particular graph, okay, um, how many regions do I have? So R1, R2, R3, R4, and outside is R5. So total 5 regions. Number of vertices is 4. Number of edges is 1, 2, 3, 4, 5, 6, 7. Yeah, 7 edges. So V minus E plus R is V. 4 minus E is 7 plus R is 5, which is equal to minus 3 plus 5, which is equal to 2. So this property is satisfied. Okay. Now, this is another property that should be satisfied. 3 times R is less than equal to 2E. So 3 times R in our case is 5, is at most 2E, that is 14. Oh, is there something wrong here? Yeah, it shouldn't be 2E, I think. 3 times 5 is at most 2E. 3R is at most 2E. E is 7 here. Region is 5. Okay. I'll look into it. But in the meantime, let's look at this question, okay, which is not using that actually. A graph on 12 vertices has 6 regions. What is the number of edges in the graph? Oh, okay, and I forgot to mention that this graph is planar. A planar graph on 12 vertices has 6 regions. The number of edges in the graph are okay, Akansha says B. Okay. Okay. This is B. Others. Planar graphs on 12 vertices and 6 regions. I mean, this is a direct application of, these formulas. 3 is 16. Which is B. Yeah. Okay. Okay. Yeah. Yeah. Good. The answer is 16. Why? Because we know that the graph is planar, and we know that it has 12 vertices and 6 regions. Then we'll directly use the formula V minus E plus R equals 2. Since the graph is planar. Since graph is planar. Right. Now, what is V? 12 vertices minus E plus how many regions? 6 regions equals 2. Now, 12 plus 6 is 18 minus E equals 2, which means E is 18 minus 2, which is 16. So the answer is B, 16. Okay, nice, good. Now we'll kind of use the same formula for this, okay? But in a slightly different flavor. So G is a connected planar graph with 10 vertices. If the number of edges on each region is 3, then the number of edges in G is. So this is a nice question. So if the number of edges in each region, so what do I mean by number of edges in each region? So if this is a region, there are 3 edges covering the boundary of that region. Okay. So if this is something like this is not there, they are saying a region which is covered by 4 vertices. So they are strictly saying it's 3 vertices. Can we count the number of edges? That is what we are asking. So slight application of combinatorics here. G is a connected planar graph, 10 vertices. Number of edges in covering, bordering any region is 3. Then the number of edges in G, total number of edges is. Okay, someone has just joined. Yeah, Vijay Raj, we were doing this formula V minus E plus R equals 2 for a planar graph where R is the region. Okay. So this is the question. If G is a connected planar graph with 10 vertices, number of edges bordering each region is 3, then the number of edges, that is what we need to count. Okay. Okay, I'll give you some more time to think about it. Okay, so let's look at this question. So we are saying it has 10 vertices. Okay, for now forget the fact that it has 10 vertices. Just look at this particular point. Okay, number of edges on each region is 3. So if this is a region, then there are number of edges in the region is 3. Right. First of all, it is connected, so I cannot do something like this. Okay, it needs to be connected. So for example, here this is still valid because this is a region with 3 words, but something like this is invalid, right? Because this particular region has 4 vertices, 4 edges. So here, so it will look something like this. So now we can see that maybe the number of edges actually depend on the number of region, because as I'm increasing the regions, the number of edges are increasing that way only, right? So we can see that for every region there are 3 edges surrounding it, right? For every region there are 3 edges surrounding it. Now you might say that, oh, okay, then if R, okay, then if number of regions, okay, times 3 equals the number of edges. You might say this, right? Number of regions times 3 is the number of edges. But there is some overcounting happening here. What is the overcounting? For this, I'm counting 3 edges, right? For this, I'm counting 3 edges. For this, I'm counting 3 edges. But in the 3 edges that I counted in this, I'm counting for, I'm overcounting for this region also because they are sharing edges. So here also I'm overcounting. So across two regions, I'm sharing, one edge. I'm overcounting it twice, therefore. So I need to divide by 2. Now I have an accurate count. Okay. I'm telling you that, each region is bounded by 3 edges. Now these each edge, okay, is shared by 2 regions. So if I simply do number of regions times 3, then I'm overcounting, right? I've already counted this edge. Let's say I've already counted this edge, but I'm counting it for this region also, I'm counting it for this region also. So I need to divide it by 2 to remove this overcounting. So now what I do is, so which means that number of edges, which is E, is equal to 3 times R by 2. What is R? Okay, we don't know that. Is equal to 3 by 2 R. Okay. And number of vertices, what is number of vertices? 10. So now since the graph is planar, I'm simply going to plug in the formula now. V minus E plus R equals 2. So V is 10 minus E is 3 by 2 R plus R equals 2. So now what is R? Or since I need to do it in terms of which means R equals 2 by 3 E. So let me write minus E plus 2 by 3. I think this is better. So 10 minus 2 is 8 minus E plus 2 by 3. E is 1 by 3 equals 0. So E equals 3 times 8, which is equal to 24. So 24 is B. So the answer is B. Okay. Is everyone clear with this? So there was a small combinatorial result involved. So, we were trying to show that, number of edges actually depends on the number of regions. But when we were counting the number of edges with respect to the regions, each edge was getting counted twice. So to remove that overcounting, I'm dividing it by 2 because it was getting counted twice. Each edge was being counted twice. And then then we got this. We got this, okay, and simply put it in this V minus R equals to V minus E plus R equals to. I hope it is clear. Okay. So is it fine, Akanksha, Divya, Gomati? If you want me to repeat it, then let me know. Okay. Okay, Akanksha, okay, good. Others, I hope it's fine. Just let me know if you want me to repeat it. Okay. Okay. I hope that means yes. So also this previously I think this did not work, okay, because this is not a simple graph. There is, there are, this edge and this edge are between two edges between the same set of vertices, so this will not work for um, this formula will not work for this graph. So, but if we remove this edge, then I think the value, because we are removing one edge, so one region is also getting removed. So we have, yeah, this is load. Okay, just to correct this, this will not work for this particular, this inequality. Okay, so moving on. Now we are approaching the end of this discussion. There are just two more questions left. Okay. So graph coloring. Now this is another rich area of graph theory. Okay. So the idea is that, if I have a graph, you can color it with your favorite colors. I can put a red here, I can put a red here, let's say. I can put a green and a green here. Okay. Now this is a coloring of a graph, but this is what is called an improper coloring, or not a proper coloring. Okay, what is a proper coloring? This, and this, and green again, let's say. This is a proper coloring. Why? Because no two same colored vertices share an edge. You can see that, this green vertex shares an edge with red, is connected to the red, and that is allowed. Green is sharing with blue, that is allowed, but green sharing with green is not allowed. For example, here, green is sharing with green, red is sharing with red, red is connected to another red vertex. This is not a proper coloring. So, well, you can always say that, oh, okay, what I can do? If I have a graph with 4 vertices, then I can color this red, I can color this green, and I can color this blue, and I can color this pink. Well, this is proper, but not what is called minimal. That is, I can find a coloring set, I can find a set of colors which will do it in fewer than 4 colors, and clearly this is doing in fewer colors. Okay, so the smallest number of colors needed to color a graph properly, proper coloring, meaning no two edges have the same color, no two adjacent vertices are the same color, properly is called the chromatic number, also shown by chi of G. Least number of colors required to color a graph. For example, if I have this graph, then to properly color, how many do I need? If this is red, as soon as I put this as red, the other two edges, okay, I need to choose a different color. So I'll choose a green here, and below red I can choose a green again, and I can choose a red here, but I cannot do lesser than this. I cannot choose, one color, because if I choose a one color, then obviously two edges will be colored, two adjacent edges adjacent to each other will be colored with the same color, and it will violate the condition. So here chi of G is equal to 2. This is the least number of colors I need to color it properly. Let's call this graph G. Okay, so this is about coloring. Now we'll try to solve this question. So you can experiment with this. What is the chromatic number of the following graph? 2, 3, 4, 5. What is the least number of colors that I would need to color this graph properly? Properly meaning no two adjacent vertices. Okay, Divya says 3. Okay. Okay. Let's see. Answer is 3. Okay. Okay, good. Yeah, that's a great answer. So let's try it. Let's say I just color this one red. So immediately C and B I cannot color red because it would not create a proper coloring. Two adjacent same colors would be there, same colored words. So let me choose green. Okay. So let me color C as green, and oh, you know what? Then I can use green on B again. I can use green color again. That's good. I want to minimize. And in D, I can use red again. So that's good. So far I've only used 2 colors. Now let's look at E. Okay. I cannot color E as red, because if I color it as red, A is connected to it and it is not proper. I cannot color it green also, because B and C, it is adjacent to B and C and it is colored the same. So I need to use another color, blue. So far I've used 3 colors. Now if you observe F is connected to E and F is connected to B, which are both blue and green respectively. So that means I can use red color now, because F is not adjacent to a red colored vertex. So how many colors have I used? Answer is B, 3. I've used 3 colors: red, green, blue, and you can verify that it is properly colored. Good. And finally we move to the final question of this session. Okay. So the question is as follows: which of the following statements are true about colorability? Every cycle is 2 colorable. What does it mean to be 2 colorable? The chromatic number is 2, or in other words, the least number of colors need to properly color that graph is 2. Every cycle is 2 colorable. Okay. Or rather, actually, not proper coloring. 2 colorable means that I can just color it with 2, not necessarily proper coloring. Okay, sorry. So yeah, every cycle is 2 colorable. Can I color every cycle with 2 colors? every bipartite graph is two colorable. Can I color every bipartite graph with two colors? Every tree is two colorable. So can I color every tree with two colors? So which of these statements are correct? Okay, Akanksha says B. Okay. So others also. Okay. Okay. Yeah. Divya says D. Okay. Finally, Gomiti. Okay, Akanksha said B. Okay, statement 2 and 3. Okay. Oh, okay, sorry. This should be statement 3. I gave it just 2. Okay, let's see which ones are the correct statements. So let's see the first one. Every cycle is two colorable. Every cycle is two colorable. Okay, let's see an example of a cycle. This is C4, right? A cycle on 4 vertices. Now, can I color it with two colors? We already saw this, that it is actually possible to color with two colors this way: red and then green. But let's not stop here. Let's go on. Let's look at a cycle with 5 vertices. Okay, a cycle with 5 vertices, and let's use the same logic. Let's alternatively color with red, then green, then red, then green, and if I go with a red again, we have a problem here. Why? Because these two edges are colored with the same colors. But if I had chosen a green instead, okay, if I had chosen a green instead, then again I have a problem. Right? So there's a problem here too. So turns out that I need to use a different color to color this. So finally we realize that, if I keep doing this process, now if I look at C7, then I can use the same logic here. I can alternatively do red, green, red, green. But as soon as I do, sorry, C6. So as soon as I make it C7, I have a problem here. I'll need 3 colors. So actually, I'll observe that even cycles are 2 colorable and odd cycles are 3 colorable. Okay, so the statement that all cycles are 2 colorable is actually false. Statement 1 is false. All cycles are not 2 colorable, and counter example is C5. Counter example. Okay, now let us look at statement 2. Every bipartite graph is 2 colorable. Now in a bipartite graph, I can create 2 partitions of vertices, let's say like this. This is an example. Well, here you can actually conclude it easily that this is actually indeed two colorable, because I can color all the vertices in the left with one color and all the vertices in the right with the other color. So as soon as I see this, I can tell you that, oh, okay, this will be a proper coloring. Why? Because since one partition has a single color, and since it is bipartite, I cannot have an edge between vertices of the same color. So I don't have a violation of the property of proper coloring. Whereas even if it is connected to another vertex, it will be connected to a vertex of some other partition, and that color is red. So it is still fine. So statement 2 is true. In fact, this is an if and only if condition. If it is two colorable, you can do it in the other direction. If it is two colorable, then it is bipartite. This is a good exercise if you want to try. And finally, statement 3. Every tree is two colorable. And here, actually, I mean, doing a proof would take some time, but I'll just give you the logic here. Okay, so you can do it experimentally also. This is a tree, right? So I can color this one red, and I can color this one and this one green, and all is fine. And let's take a more complex tree. What does it mean to be a tree? There are no cycles in it. So this is a tree. So what can I do? I can color one vertex red, and whatever it is connected to, I can color it green, and I can color the others red. Sorry, this one should be green. Green, and of course red. So this is also two colorable. Well, what is the idea actually? Think of a tree to consist of levels, okay? I can always draw a tree to have some kind of hierarchy like this. This is more like a data structure, but this is one way to think about it. So draw a tree this way, and in each level, keep alternating the colors. So this will be the red region, and this will be the green region, and this will be the red region, and this will be the green region, and this is the red level. Well, the idea is that if two vertices, now you've colored the tree this way. Now the idea is that if I have two vertices of the same color adjacent to each other, if they have an edge between them like this, then it no more becomes a tree because I have created a cycle, and trees are not supposed to have cycles. So this kind of thing will never happen in trees. So rest assured, I know that if I color it this way, I can definitely color with two colors. This is a proper two coloring of the vertex. Okay, so statement 2 is true, and statement 1 is false. So the answer is B. 2 and 3 are true. Okay, let me see the answer. Yeah, Akanksha and B. So Divya said all 3 are true. Yeah, so Divya, the problem was in statement 1. Okay, I hope it's clear. In statement 1, if you consider a cycle with odd number of vertices, then Divya, now clear, sir. Okay, good. Yeah, if you take an odd cycle, then you can see that it's not two color. Um, okay, if you have any questions, let me know. But we've come to the end of the session, so I don't have any more questions to discuss here right now. So, if you had any difficulty understanding any of these questions or any of the topics in the lectures, then you can stay back and let me know. Otherwise, you are free to leave. Okay, and we can meet again Tuesday, 6 p.m. The same time of the week. Okay. Okay. Thank you, Akash. Yeah. Okay. Thank you, Divya. Bye. Okay. Thank you, Gomati. Bye.